and we have something called electromagnetic. And then the electromagnetic too, we have something called the electromagnetic spectrum, which contains all the radiations. So as of last week, we were talking about 7 different radiations. And if you remember, we tried comparing these radiations in terms of some quantities, which is very important. Exactly, some quantities. And as at what we have done so far, we compared it with 3 different quantities. That is the wavelength, their energy, and their frequency. Exactly. That is what we've been talking about. So along a good arrangement of these radiation, we can know which of them has more energy than the other, which of them has more frequency than the other, which of them has more wavelength than the other. And these quantities, that is going to help us define their properties, define what they can be used for and all. Is that okay? So you know that, of course, high energy will be very helpful. But at the end, we can use it to generate energy. Let's say electricity. We can use it to generate nuclear weapons. We can use it to treat some diseases. Is that okay? So these properties are very important. Now, we talked about a whole lot of these things, where I tried explaining the fact that each radiation has its own application and the harmfulness of it. There's this thing that we didn't talk about, but I'll bring it up later. Is that okay? So, and we ended up with something called the light matter interaction, where we said that when light interacts with matter, a lot of things do happen. And when you say light matter interaction, we are talking about any of these radiations. Is that okay? But particularly, we are talking about visible light here. Is that okay? When it interacts with matter, and matter can be in any other form that you can think about. It can be a solid, it can be a gas, and it can be a liquid. Is that okay? A lot of things happen. When light is incident on it, the light can be reflected, of course. The light can be absorbed. The light can be transmitted. The light can be scattered. The light can be interfered. Is that okay? The light can be refracted. Is that okay? So all these things are the things we want to look under what we are talking about. Is that okay? Under the interaction of light waves. And we did a little brief discussion about interference, which I'll go details today. We did a little interaction about absorption and scattering, which I'll go into today. Then today I want us to start with the reflection part. Then I'll end with reflection. If it's possible, we do refraction. I'll end with refraction. Then I'll go back and do the absorption, the scattering, the diffraction, then interference. Is that okay? Then that will be all for today. Hopefully next week when we come back, then I'll come and do the heat aspect. Then we'll be done for this particular course. Please, do we all agree to this?
Yes, please.
Perfect. So, okay, so let's all go on. Then let's see if we can finish something today before we end. Okay, so one way or the other, we are all very familiar with reflection and refraction because we have done a very lengthy conversation about it during our general physics 2 class. Is that okay? So some things is going to be a recap, but some things that you didn't understand, maybe appreciate it right now because it's going to be a build up here. Is that okay? And if you remember, when we were talking about reflection, we spoke about the fact that if we have light and this light is moving, it's always moving in a particular direction. Is that okay? So we need a way to signify or demonstrate its direction of movement. And that is what we are going to call the ray. And the ray just showing the very narrowest of light. Is that okay? But ideally, it's not like this. But in a physical presentation form, this is how we do it. Is that okay? So what we do is we draw a line, a very straight line. Then we use an arrow to show the direction in which is what is moving. And this is what we call what? A ray. And of course, everyone that sees this one knows that it's going this end. When you look at the diagram I have down here, you know the arrow has been at the tip here. It's not correct. Is that okay? It's supposed to be at the middle here. And this is what we call a ray. But a collection of them too has a name. And here we call it what? A beam. Is that okay? And again, the arrow here is not correct. Is that okay? It's supposed to be at the middle here. And if we have something like this, of course, that one too is showing us that it's moving in this direction. You know, this beam can all be in a parallel manner, or they cannot, or they can also be in a form where at the end of the day, you know, when you have the parallel manner, there is no way the ray is going to meet. Is that okay? We can also do it in such a way that we change the angle a little, and it's expected that the ray should meet at a particular focal point. Is that okay? And when we do something like that, we are not going to call it a parallel beam. We are just going to call it what? A converging beam. Is that okay? And as the English name says, like if you are in a class, you tell the class, please, we are all converging at 1 a.m. in the playgrounds. Is that okay? It means we are all going to meet up. Is that okay? So we are converging. We can also diverge. Let's say after having a meeting with your students in school. Okay, now let's all diverge. Is that okay? So it means anywhere they are coming from, they should move back to that place. Is that okay? And that one, the arrow is represented like what you have here. So this is a diverging beam, this is a converging beam. In terms of ray display, if I have a bulb, this is my house. How am I drawing this house? Okay. Then I have a bulb in my room. So let's imagine this is your room right now. The bulb that you have there, is it behaving like a parallel beam, a converging beam? Sorry, a diverging beam or a converging beam?
Diverging beam.
Diverging.
Diverging. Is that okay? So it means all the light source is coming from one point. Is that okay? So the arrow can be at the middle here. Is that okay? So this is a diverging beam. Very, very good. Exactly. But let's look at a very typical example. If, I don't know if you've ever tried this one, we can use a lens in the sun, a very sunny day. Then we can put a paper behind the lens like this. And if you're able to get a very good focus of the light rays coming from the sun through the lens, we can get it at a very sharp point here. And if you don't take care, with time, it may even start burning the paper. Has anyone tried this thing before? Okay. So it's a very nice demonstration for kids and all. This kind of rays or light that is moving from the lens to the paper here, is it behaving like a converging beam, a diverging beam, or a parallel beam?
Converging.
Converging.
Converging beam. Perfect. So they are all converging at a particular point here. Is that okay? Now, let's look at something. Another typical example. If a teacher is teaching, and I don't know if you've seen, sometimes they use a laser pointer. Is that okay? So, like how I'm using pen to teach, they use a physical laser pointer. So even if the teacher is here, and the teacher wants to show you something on the board, the teacher don't have to necessarily walk to the board. He will use a laser pointer. The laser is holding him, and it has a point here like this, the beam of light like this. And you see the same size of beam of light here. That is using to show you, like what I'm using to show you on my screen. Is that okay? Something like this. Are we having a converging beam, a parallel beam, or diverging beam?
Parallel.
A parallel beam, perfect. Is that okay? As far as the beam of light is like this, and it's the same as the one on the screen, it's parallel. If it's different, you will see it, this one being bigger than this or being smaller than this. Is that okay? So that's a typical example of a parallel beam. Now, in terms of presentation, we can also talk about something we call the loss under this reflection. And a very typical example is all what the very common one is what we all know, and graphically displays like this. No, schematically displays like this, where we have our incident ray, the normal, and the reflected ray, all lying at the same point of incidence and on a plane mirror. Is that okay? So this is the very common law of reflection. And another one that also we can talk about is these angles. Is that okay? You have to know that always this angle is supposed to go at the same, whatever being the case. You may not get a very straight line. Sometimes you may get a crooked line like this. But at the end of the day, when we get a reflection coming here, an incident light coming here, because the surface is rough, we may not get exact angle of normal to the perpendicular, right? So we may get maybe something like this going on here. Then this is our normal. So you can see that our normal is not the same, but whatever being the case, we have to know that this angle and this angle is the same. Is that okay? It could be that we can get another rough surface like this. Please excuse me, hold on. Yeah, Doc. Good morning, Doc. Okay, sorry, thank you. So it could be that we can also have a rough surface like this. And our normal may not be straight as we want. Our normal may be presented something like this, as I showed you earlier. And our incident angle is going to be something like this. And the reflected angle is going to be something like this. Whatever being the case, this angle and this angle should be the same. It's okay. That is the incident angle and the reflected angle should be the same. It is a law under a reflection. So we cannot remove that at all. It's supposed to be there, right? So these are the two laws. And even on a reflection too, we can also talk about their types. Is that okay? Where we can have a regular, where we can have, please hold on. Yeah, hello class. Please don't go offline. I am changing my laptop for Dr. Peter to use it for another class. So please don't go offline. I'll go offline for a minute to change my laptop. Is that okay? Then I'll join you very soon. Alex.
Okay.
Okay.
Do you agree to that? Very
Yes.
good. Um, Abel, can you see my slides?
Yes, please.
Yes, sir.
Yes, please.
Okay. Sorry for the interruption. So yeah. So I was talking about the issue of law of reflection, which is also very important for us to know and understand. And under this reflection, we have specular and we have uh, diffused. And this is very important because even when you are like furthering your master's or say doing a PhD, there's a study that we call specular reflection spectroscopy, diffuse reflection spectroscopy, which is the same basic principle we are learning now, but we've dived a little deeper into it. Is that okay? We've dived a little deeper into it. Is that okay? So it's the same principle. But we see how this diffuse or specular reflection, their angle and the surfaces are, they still apply into these further studies because that is going to influence you whether the subject of study you are going to use diffuse reflection or specular reflection. Exactly. But to our level, when you're looking at these two types, you're looking at their surfaces. Is that okay? How smooth the surface is, how rough the surface is. If it's very smooth, we are calling it a specular reflection that is happening. If it's very diffused, that is the surface is very rough. And look at the 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 specular reflection. How I'm coming. How their normal is going to be. If this is the reflect incident and this is the reflected, the normal is appearing around this end. The normal is appearing around this end. The normal is appearing around this end because we know that at the end, for a law of reflection, this angle is supposed to be the same as this angle. This angle is supposed to be the same as this angle. And lastly, this angle is supposed to be the same as this angle. Is that okay? So it is important we know all this. And look at relatively comparing it to diffused. We're expecting the normal to appear around this end. We're expecting the normal to appear around this end. Look at how this one is. They are expecting the normal to appear around this end. For this particular line, so we're expecting the normal to be around this end. Someone may ask, how am I tracing the normal? The normal is supposed to be between these two angles, the middle one. Is that okay? Because we know that for the law of reflection, the incident angle is supposed to be the same as the what? The reflected angle. So I have to choose in between the two rays. Is that okay? And here, this is the two rays. I'll choose between the two rays. And here, this is the two rays. I'll choose between these two rays. And here, this is the two rays. I'll choose between these two rays. So you can see how ununiform the surface is, causing the different normal to have a different position. They are all not perpendicular. Unlike the specular, you see they are all very straight, exactly, and perpendicular to each other compared to the plane. Exactly. So it is important to know that. Now, another thing that we have to also know is when we have a plane surface, what are some of the properties that we are expecting to get? Is that okay? And we looked at this. We said that if you are standing in front of a mirror, it's going to be abstract, it's going to be virtual. We are expecting your size to be the same as the image. We're expecting a literal inversion. Is that okay? So we've done this. And I think we went through this one too. Do we have to still do it again, or you are good so that we can move fast a bit?
I think we are good.
Okay. So that is for Frank Paddy. Anyone who has an objection to that? Because I think I wanted to just skip all this one, but someone said they still need that. Yes, Sir Abdul. You have to start.
Let's move there. Please.
There's another trial question here that we can do. But when it comes to image, formation, there's two important types that we can look at. We can look at one that we call a raw image. We want to look at one we call a virtual image. Is that okay? And the last time I was explaining this, that when you look at a raw image, it can be formed on the screen, as simple as that. We can literally let this image form on our palm, or bring a paper, let it form on it. Bring a cloth, let it fall on it. We can literally let it form on anything that we want. And the typical example is using a projector. You can let the image fall on anything that you want. Compared to a virtual image, it's not like that. The image is formed within something. Is that okay? And that is the issue for virtual image. So anytime you see an image formed within something, it's a virtual image. Like the plane mirror. Your image is formed within the mirror. Is that okay? Like the TV. You see an image, but the image is within that TV. Is that okay? So that is what a virtual image. But if we can let the image fall on anything that we want, it becomes a raw image. And we also spoke about reflection. And reflection too dates back from the Arab scientists, and down the years we have this. Is that okay? We can think about the fact that if we have a light that is travel in air, it's very fast. Immediately it enters water, it travels very slow. It exits, travels fast again as before. So that was the whole conspiracy around refraction. Is that okay? And that is what dated back, and now we have a principle like what we have here. And now we know that anytime you are talking about refraction, we expect an incident ray. We expect normal as the same as a reflection. But this time around, there's something we call the refracted ray, which we have to consider. And this thing is very important because at the end of the day, their movement is really, really dependent on how the medium is. When I say their movement, how big this angle is going to be, or how small this angle is going to be. If you are from a denser medium to a less dense medium, it's going to be different. And if you are from more dense medium to a lesser dense medium, the angle is going to be different. Is that okay? Situation like this, we're expecting the angle to bend towards the normal. Is that okay? Situation like this, we expect the angle to bend away from the normal. So that is the differences that we have there. Another thing too that it may interest us is some formulas that we can also bring in place in such situation. This is a very common formula, N equals C V, where the C is the speed of light, and the V here is the speed in that medium. And if you have this formula, we can find the refractive index of the medium we are talking about. Nevertheless, even if we have the wavelength between the two of them, we can still find our refractive index. Now, another thing that is of interest is that anytime we are talking about Snell's law, we have to also consider this formula. N1 sine I equals N2 sine R. And I don't know what was going on during exams, but there was a question under, I think, dispersive power. And a lot of people was using this kind of formula to solve for that. And some was even using the N equals sine into bracket, the minimum deviation and the angle of the prism. And I was so confused about that because the question was very clear. And there's no way we can find the dispersive power from that kind of formula. So I didn't know how it was starting and how it was ending in that perspective. Anyways, so let's be careful the way we use these formulas. Is that okay? We are asked to find a parameter. What are we deriving from here that can give us that parameter? That is the most important thing. So let's say we are asked to find the speed, but can we find speed here? No, speed is not here. So if speed is not here, which formula can N relate that I can get speed? Is that okay? So I know that anytime I have N, it can also relate what C over V. Then if that's the case, I can come and do substitution here, come and do the same substitution here. Is that okay? And because C is C is C is C, I can cancel the C out and get a formula like this. Relatively, this is fine. Is that okay? You want to do a little show off, you can write this formula, bring the substitution and come and end up here, which is very fine. Is that okay? But sometimes the deviation is too much, so we have to be careful. Then there's another thing that we also have to know. Total internal reflection. And I think something like this also came in your exams, I guess, where you were you asked to explain total internal reflection and draw something? I don't know. Can you hear me?
Yes, sir.
No. Okay, that's fine. I got a chance to look at your script, but I don't know if this one came. So there's another thing that we have to also look at. What we call the critical. And when we are talking about internal reflection, we are talking about the aspect where I have a medium that is traveling from a denser medium to a less dense medium. But with time, I tend to increase the incident angle. Is that okay? And anytime I increase in the incident angle, ideally, I'm also expecting the reflected angle to also increase. Is that okay? A time will come, this refracted angle will increase to the extent that it will be at 90. It means this line is going to lie on the Y, something like what we have in this diagram. Is that okay? And in a situation like this, I'm saying that my refracted angle is what? It's 90 degrees. Anytime you have the refracted angle as 90 degrees, it means again that your incident angle has reached a point that we call the critical angle. Is that okay? So you reach the critical angle, the only thing left for us to do is that anytime that we have the critical, it means that we can derive a formula like something like this, the normal Snell's law, make N1, N2, and this one, this other. But this time around, the R here is what? It's 90. So it's like 90, we are going to get 1. So this one goes off as 1. And that is what is given as this formula. Is that okay? So if we have something like this, it means that anytime I exceed the critical angle, I'm going to get a reflection because the angle here is still increasing. Is that okay? So it means when I exceed the critical angle, this time around, my angle has exceeded to this end. It is no longer refraction. It is what? Reflection. Is that okay? And I told you that this one has tons of applications, a lot of them. Is that okay? Like a very typical example is the fiber optic cable and all. And there are some formulas, these are the applications, there are some formulas we can look at, some questions we can look at. And I concluded here, then I think we jump straight to Fermat's principle. Please, those who said they don't understand this particular part, in case I reach a point and you don't understand, just draw my attention, then I'll take my time. Is that okay? I'll still be going as a recap. So Fermat principle is very important. And if I remember very well, I did an illustration showing you how Fermat principle behaves. And I told you that if we have a path and one is shorter, there is no need for us to go through that long path. And that was the whole idea of Fermat. Fermat is saying that if reflection is going on, we have a plane and we have a normal, and reflection is going on, it hits here, it goes. If I have something like this, why worry myself go through to the normal, to the point of incident before I go again? Why can't we just go straight like this? Is that okay? That is the whole principle of Fermat. So he was using that ideology to prove for the law of what? Reflection. And it's important. So now, if you have something like this, it means that if I have a point A and a point B, A is traveling to point B, but through the law of reflection, it has to get to the incident, the point of incident before it goes to B. So we can denote some parameters where we can say from this end to this end is our H. From the length of the A to the P, the point of incidence is our X. Then the whole distance traveled is our L. The point of incidence is our P. And because we have the whole distance traveled and the X, when we subtract, we're supposed to get the whole length of what? Of B traveled. Then we can get the height of what? Of B. Are we following? Now, if that is the case, it means that I can also denote some parameters for the angle of incidence and the angle of what? Reflection. So these are the parameters we are going to play around. These are the parameters we are going to play around. Now, if you have something like this, now let's look at this. We can use Pythagoras theory for the first time. Is that okay? Where we know that anytime we have something like this, A, B, C, where we can say C is equal to what? The square root of what?
A squared plus B squared.
Thank you. A squared plus B squared. Are we good? So now, if we have something like this, we can implement the same thing in what is going on here. Now here, our situation here, the C here is going to be AP, this whole distance to P. And our A here is going to be our HI. And our B here is going to be our X. Is that okay? So we have our H squared, our X squared. We have our square root there. And the C representation is the AP. And that is what we have here. Is that okay? We can do the same thing for the distance traveled here. That is for P to B. And we know the distance here as L minus X. We have the distance here as H squared. Is that okay? So we have H squared plus LX squared. And we have our square root, all equated to what? PB. Is that okay? Now, my interest is to find the whole distance covered from A to P P to B, it means I can add these two distances together. And that is what is going to give me this. Now, if I have a situation like this, it's going to be straightforward a bit because at the okay, so Bismarck is saying I should take it slow. Okay. So it means that if I have a situation like this, I have to actually like I can find a distance and I can actually use our normal procedure as in the velocity to also evaluate this. We know that velocity is always equal to what? Distance on time. And if I want time, it's going to be T on what? D on V. But you have to know that here, the speed of the material is light that we are talking about. Is that okay? So we can just bring C here to replace that. Is that okay? So if our situation here, you know this end was D. If we remove the D and we replace it, we are going to get what? TC. And if I make only T the subject, it means it's going to be T equated to this whole equation on what? On C. And that is how we manage to get this. Is that okay? Now, we can equate this one to with respect to time. Okay, we want to know the time that A used to reach B. Is that okay? And that is what we were trying to look at here. Now we can find the derivative with respect to T and what? And X. That is time and the distance that is used to travel. And the last time I was teaching you how to do this derivative thing. Exactly. I don't know if you had the chance and the time to go back to look at it again. Did you do that? Or the time wasn't available?
Yes, sir.
So which of them? Is it we didn't do it or we did it or the
Sir,
time wasn't available?
I couldn't do it.
Mm. And any different person? Anyone? Did anyone look at the derivation of it? Okay. No answer means we didn't try. That is fine. But the last time I was trying to teach you how this derivative works in terms of having a square root. Let's say you have a value. Let's say someone is complaining not seeing the screen. Can you see my screen?
Yes, please.
Okay. So Jeremy, I beg you check your connection. I was teaching you how in mathematics, if we have, let's say, h squared plus c x squared, and you know we had this whole thing is a square root of it, which is the same as 1 on 1 over 2, 1 on 2, sorry. And if you are finding the derivative of this, the first thing you have to do is to bring the 1 over 2 down here. You finish, subtract the 1 over 2 by 1 again. Then you find the derivative of what is inside here. Is that okay? So now we have 1 over 2 here. And because you are finding the derivative of x, you find what is inside here. The h squared is a constant, so it goes 0. But we can find the derivative of the x squared. Then you get what? 2x. Then when you finish, you have to bring this whole term again. That is going to be a squared plus what? X squared. But this time around, we've subtracted 1 from the exponent. So we are going to get what? Negative what? 1 over 2. So if you have situation like this, 2 here can cancel this 2. It's left with our x here. So we can write our x. But look at the term here. if we have any value 1 over 2, is the same as what?
Square root of
Square
x.
root. If we have the same number, something like this, but negative 1 over 2 is the same as what?
Negative square root of x.
Negative square. That is going to give you an imaginary. It's the same as 1 over
Oh, okay.
square root of x. Is that okay? This is very important. So if I have a situation like this, it means I can bring this whole thing to the denominator. I have my x here. The x is written here. And I bring my denominator here. A square root of what? H squared plus x squared. This is for the first term. This first term. If you find the derivative of this first term. Let's look at what we are getting. So you see what we have here. X over square root of a squared plus what? S squared. And our c remains there because there's a denominator of c there. So this is our first term. Now let's look at the second term. Let me clean what is on the board first. So now this time around, I have another square root. So I can remove the square root, then just do h squared plus L minus X squared. And the big bracket comes 1 over 2. Please, did we all understand the first derivation that I did?
Yes, please.
No, sir.
Okay. So let me
The
go
problem
through
is with the derivative. How to find a derivative of those things is a problem.
So I'm going through for the last time. A lot of people has their own ways of going through having a situation like this. Instead of this, they can make this one represent U and V and other things, and they are very okay with that. Is that okay? But I do it straight away. Is that okay? For simplicity's sake, in my situation. In general, I'm using the first term again. I've been given this h squared plus s squared. Sorry about my handwriting. 1 over 2. Everything that is going on here, I'm using the rules to do it. Is that okay? And the rules under finding a derivation of this, the first thing is very important. And the first thing is telling us that anytime we have a situation like this, first thing first, subtract 1 from the exponent. Bring the exponent down here. That is the first rule. So we have to bring the exponent down here, 1 over 2 down here. Is that okay? The next thing that we have to do is to find the derivative of everything that is inside here. Is that okay? If I'm to find the derivative of 1 with respect to, let's say x, 1 is going to give me 0 because there's no x attached. If I want to find the derivative of x with respect to, of course, x, I'm going to get what?
1.
I'm going to get 1. If I want to find the derivative of, say, 2x, I'm going to get what?
2.
2. If say I want to find the derivative of, say, x squared, I'm going to get what?
2x.
2x, perfect. And this is very important. Now, if I'm finding the derivative of what is inside the bracket, a squared is We are finding derivative with respect to x, not h. If we are making respect to h, it means the h should be relevant. But here we are finding the derivative with respect to what? X. So it means our h here is what? It's a constant. Straight away. We don't have to stress ourselves there. So now, if h squared goes at 0, the 2x will still remain. Is that okay? We find the derivative of s squared, we get what?
2x.
2x. So I'll multiply this one, the 1 over 2 I have over already, as by 2x. Now I'm done. There's no sub 10 inside there. Supposing there's another into bracket somewhere inside that has 2x or that has x inside, I would have find the derivative again. But there's nothing like that. So that is all. Then when I finish, I'll bring the whole thing again. That is my h squared plus what? X squared. Now, if I have a situation like this, the top there, I have to subtract 1 over 2 minus 1. And I'll get what? Negative 1 over 2. Now, if I have this, my 2 can cancel this 2. Now, I'm going to get what? X. And this whole thing here that I have here, that is containing the 1 over 2. Negative 1 over 2. That is what I brought it down here. And I was explaining it on the, look at the right side here. Anytime we have x1 over 2 is the same as square root of x. Anytime we have x, negative 1 over 2 is the same as 1 over the square root of x. Here I have a value here all over, all raised to the power negative 1 over 2. So it means I can bring all of them down here and square root it like this. That's what a squared plus x squared. Are we okay a little?
Yes, sir.
Yeah. So Abdul, it's not Abdul. Mumuni. He wrote at the comment section that he's not getting it. How is it now? Okay. So now let's look at the next term. So that was the first term. Let's look at this next term, this term. How we manage to get this next term. So I'm going to leave this one for the class. I'm giving you only 5 minutes. Try your hand on this term for me. This term. Find the derivative of this one. That is the dt on dx for me. Can we do that right now, please? Don't look at the answer and come and tell me. Do it yourself, I beg.
Hello, sir.
Please, are we done?
Yes, sir.
Okay, perfect. So, Sir Kwabena,
Yes.
will you guide us through how you managed to get it? Or better still, hold on. Apart from Sir Kwabena, do you have any other person who's done?
Hello, sir. I'm also done.
Okay, so two people done. Can we get more hands? Are we trying, please? Okay, Yakubu 2 is done. Two more hands. Okay. Sir Yakubu, will you take us through? Sir Yakubu, will you take us through? Who again is that, please? Are we doing it? Or we are waiting for answer? Okay. Sir Charles, are you doing it? Or you are done?
I'm doing it.
Okay. Say Azuma, Peter. Say Azuma, are you online? Say Bafo. Bafo Chireme.
Hello, sir.
Yeah. How is it going? Are you done?
I'm on it, sir. I lost track a bit and joined later.
Okay, that's fine. Sir Charles, you see. Oh, I just mentioned your name. Yeah.
Yes, please.
And then we have another Sir Charles too here. Charles on Mariba. This is a nice name. Sir Charles on Mariba. Okay, Sir Christopher, sorry.
Please, my network.
Sir, I'm doing it.
Okay.
I'm
Sir David.
struggling, but still, I'm on it.
Okay, we are waiting for you. Sir David Edu. David Edu. Okay, Sir Emmanuel Asante. Okay. Maybe Sir Kwabena.
Sir,
Yes, you take us through. We may take long with this, so take us through.
Okay. So I first wrote the formula, the H2 squared plus L minus S all squared square rooted. So I
Can I
turned the
hold
square
on?
root.
Did you write what you are saying?
Yes, please.
Can you do it? Show your video on it, then maybe use it to explain to us. Is it possible in your room?
I should.
Turn on a video, but not your face. Then you show your video on your paper, so that
Aye.
it will be easy for us for your demonstration. And I remember,
I remember that how to do it. I can't.
just turn on video, then show the video to your book.
To my so you see it today.
Very good. So the video, but not your face. So the video. Now the phone actually book on song, you know, so that we look at what you have there. Then we follow up.
Okay, sir.
So just turn on your video.
Please, are you seeing it?
Yeah, we are trying.
Is it clear?
It's not clear. Is it clear for everyone? It's not clear for me though, but
I think you should send the phone closer, the camera closer to the phone.
okay. Why don't you use the back camera?
Okay.
You can use the back camera. So I should leave this place. It's fine. We may take long with this one too. Don't worry. Forget about the video. You explain it to us. We may follow. Is that okay? Mm-hmm. So it may not work. Mm-hmm. You continue.
All right. So I first turn the square root. I change it to half. I hope that is it. So the first step, the square root was changed to half. Then I have the equation as I have the term as h squared or h2h squared plus l minus s all squared, all into a parenthesis and a big bracket, half, instead of the square root. Then the second step, the half descended down, or you multiplied the term here. And I also started by finding the derivatives of the term itself, the h2 squared plus l minus s all squared. So first one, the h is a constant, it goes to 0. Then tackle what is in the bracket, l minus s all squared. The 2 descend down, multiplying l minus the x. Then I took 1 from the squared. Then I have l minus x. So from that, I now also took 1 from the whole set or the whole term. So I now have all into bracket minus 1 on 2. So I have the term as 1 on 2 multiplying 2 into bracket l minus s, multiplying the whole term again, h2 squared plus l minus s all squared. Then all into bracket minus 1 on 2. So the first 2 cancels 2, leaving behind l minus x, all into bracket, multiplying h2 squared plus l minus x all squared, all into bracket minus 1 on 2. Then here, I think we have an inverse here. So taking the inverse of l minus x, all into bracket, multiplying h2 squared plus l minus s all squared, I now have l minus x divided by half of h2 squared plus l minus s squared. Then the half, I also turn it to a square root. So I now have the final answer as l minus s all divided by h2 squared plus l minus s all squared, or square rooted. Please, are you there? So the final answer again, l minus x all divided by square root of h2 squared plus l minus s all squared.
Yeah. Okay. Thank you very much, Kwabena. Lucky. Sir Lucky.
Yeah, Mr. I want you when he should snap it and send it to the platform.
Yeah. So that is what I was trying to say. Who can show his video of what he has done, then take us through? Where is Frank? Frank, you said you are done.
Yes, I'm done, but It means I have to rewrite because I did it my own way. I'm not sure they will see it.
So, like, you can show us the video as you are writing, we are looking at it.
Let me try and see.
So the video, use the back camera, then you position it up, then you'll be writing, then you'll be explaining the procedure. Is that okay? So, Seth France Kwabena, thank you very much.
Okay, sir. Welcome.
Sir, please, I'm struggling with using the back camera.
Frank, if you click on the video, let me guide you how to use the back camera. I don't know that.
Okay.
If you click on your video, or see on top where the recording is, see that on top there's some arrow that look at two arrow that are rotating on top of your phone.
Yeah.
You click on the arrow. If you click, it will take you back to the back camera. You click on the arrow.
I'm coming. Let me see what you're talking
Have you clicked it?
about. I'm not seeing it, sir.
It's on. Like the two arrow that are following each other like in a circle form. On top.
Depends on the phone. So where the volume is up there, where your where the data, the battery is beneath it, there is an arrow. There are two arrows.
Correct.
Hello? Mona. Hello.
Can we
Hello.
all see Frank's video?
Yeah, we are seeing.
Very good. So Frank, write big enough and talk when you are writing so that we will understand what is going on. Is that okay?
Okay, sir.
So I'll mute myself for you to take over.
All right. So this can also be written as h squared plus bracket open L minus X all squared, then all to the power half. So this is what we have now. And we also know that if we want to find the derivative of a squared is a constant, so it will give us 0. We know first of all we have to bring this half here as a coefficient, more or less like a coefficient here. So if we bring the half here, we are going to have.
Can you please take the phone up a bit?
Okay.
Yeah, okay.
All right. So when we bring the half here, we are going to have half multiplying. Then this is a constant, so deriving it to give you 0. Now when we come to this side, with this function here, we are going to bring the 2 to this side. Bringing the 2 to this side. So when you bring the 2 to this side, it's going to be 2 into bracket L minus X. And then with these two, you are going to subtract 1 from it. So subtracting 1 from it, you are going to get 1. So I'm going to leave out that 1. Then after this, you are going to bring the whole term again, which is h squared plus bracket opening L minus X all squared. And then we know that this, we are going to subtract, we must subtract 1 from it, which is this. So if you subtract 1 from it, then it means that the whole thing is going to be to the power negative half, which is half minus 1. Now, these two can also deal with these two. So now we are going to be left with L minus X multiplying h squared plus L minus X all squared. Yeah, to the power negative half. Okay. So this can also be written as L minus X multiplying. We know that.
Stefan, hold on. Stefan, hold on.
Okay,
After
sir.
finding the derivative of, you see, there's another bracket inside the big one, right? That is the
Yes, sir.
1 L minus X all squared.
Okay.
Is that okay? How
Yes,
did
sir.
you go about that derivative of that?
This one.
Mm-hmm.
So please, I just brought the 2 here.
Mm-hmm.
Okay, so it's going to be 2 into bracket L minus X. Then that 2 minus 1, which will give you 1.
It's perfect. But the only thing is, you have to also find the derivative of what is inside the bracket.
Oh, okay.
So consider that one too, Abek.
All right. So then this is also going to be a constant, which will give you 0. Then this is X, or let me say negative X. So when you derive it, you are going to get negative 1. I don't know if I'm right, sir.
I think it should be 2x.
Come again.
I think it should be 2x. There's a square there.
No, the square is for all of them.
Okay.
Yes. So if this is a constant, it's give you 0. This negative X, so it will be negative 1. Yeah. So, but sir, I did it the way I was doing. I had the answer.
Yeah, Frank, I better come again.
I'm saying I did it the way I was doing it, and I had the answer.
Okay. No, so the one I just told you, do it that way, and let's look at the answer that you get. I beg. Is that okay? There's
Okay.
supposed to be a negative somewhere.
So I'm saying that if it's going to be so, then it means after bringing this half here, if we bring this half here, we are going to have the half, then in brackets, this is a constant, so it will give us 0. So the half multiplying the 2 will have to come here, making it 2 in brackets L minus X. Then a 2 minus 1 will give you 1. Then with a bracket, 2, this L is constant. The L here is constant, so it will give us 0. This is minus X, so it's going to give us negative 1. So minus 1, multiplying minus 1. Then we bring the entire term here again, a squared plus L minus X all squared, all to the power negative half.
Perfect. So this is good. What you have done now is good. Class, do
Over.
you understand what he has done right now? The term he has written right now.
Yes, please.
But the only thing is, for Frank,
Yes,
you
sir.
know, someone is saying no, but you know the negative 1/2 that you've written, it is not for the entire equation. It's for only the main equation that was given to us. The derivative that you find is going to step out of that one.
Sir,
So
which
that one,
is this one?
yes, it's not controlling everything. It's controlling only the h squared plus into brackets 1 L minus X into all squared, and the bracket comes again. Is that
Okay,
okay?
okay,
So you
okay,
can bring a square bracket to control that.
okay.
So bring a square bracket today. No,
All
no,
right,
not.
then. Yeah,
Cancel the first square bracket. Very good.
yeah.
Very good.
Okay,
Very good.
okay,
Perfect. So this is how the equation is supposed to be like. So the negative 1/2 is for only that.
okay,
Is that okay?
okay,
After finding the derivative of everything that is inside, it steps out of the bracket. Are we
okay.
good? For the sake of Frank Ahin, take your time and go through this one. I beg you.
Okay, sir.
Apart from Frank Ahin, do we have someone who has an issue with it?
No, that's not
Or
good.
we are all good?
That's good.
I will not go back to explain. No, we are using Frank's explanation.
Mhm.
Okay, so I think it's only Frank
Okay,
Ahin.
so
So do it for Frank Ahin, then let's go.
all right, sir. So again, we have h squared plus L minus X all squared. So this is going to be h squared plus L minus X, that is all to the power half. Then bringing the half here, we are going to have 1 on 2 multiplying. This is a constant, so it will give us 0. Then this one is going to be 2 multiplying L minus X. Then with the brackets, the L is constant. So when we differentiate, it's going to give us 0. Then we have minus X here. It has a coefficient of negative 1. So when you differentiate, we get negative X. So time is negative 1. Yeah. Then we bring the entire term again, h squared plus L minus X all squared. But this is going to have this. we know we have to subtract 1 from the half. So when we do that, we are going to get negative half. So I think this is where we got into. Yeah, so with this, 2 is going to take care of these 2. Then we are going to have this is going to be L minus X multiplying negative 1. So it's going to be negative L plus X multiplying H squared plus L minus X squared, all to the power negative half. And we also know that anything to the power a negative function is going to be 1 over the thing. So it's going to be minus L plus X multiplying 1. It can also be written as this, multiplying 1 over H squared plus L minus X squared, all to the power half. Then we are going to have negative L plus X. This is also the same as 1 over square root of H squared plus 1 minus X squared. Okay, so this multiplies 1, we are going to get negative L plus X over square root of H squared plus 1 minus X squared. I think it can also be written as X minus L all on A squared plus
No,
1 minus
Frank,
X squared.
hold on. The negative is still in a bracket. So it's negative in a bracket, L plus X. Just keep it like that. Is that okay?
This way.
If I'm multiplying the negative through, it means L supposed to be negative, X supposed to be negative.
Okay.
Do you understand?
Yes.
I don't know why you are making only the L negative, but the negative supposed to be, just keep the negative there, then bring the brackets. So the same as, you see what you have at the top here, the second equation. So you see,
I'm thinking I made a mistake here. Because from here.
Very good. So leave it like that. So it's negative into bracket L minus X. That is all.
Oh, okay.
So the negative will step out of the bracket. Is that okay? Negative L minus X.
Okay. Negative L minus
X. Perfect. Leave it like that throughout.
Okay.
L minus X. Perfect.
So that is it. I'm rewriting it again. Negative L minus X all over square root of H squared plus 1 minus X squared.
No, is it 1? Is it L or 1?
Sorry, L minus
X. Any question to this? That is our final answer. Any question to that? Doesn't mean we are all okay. Now let's go back to our equation.
Can you be asked to prove this equation in the exam?
That is why I'm taking my time to do this. Yes, you can.
Please, in case you are proving the derivative, is it necessary, or you can just move the way it was in the way it is in the book? You need to prove all this.
The last time I was telling you that I'm the one teaching, a different person says the question, a different person marks it. let's play it safe for the marker to get our marks. You are not there to justify the things you've written. Is that okay? I am teaching you, and look at what Frank has done. I'm marking. I will know Frank's mentality and know how to mark him. Is that okay? You are not there to justify things. I don't know if you understand what I'm trying to say. So let's just play things safe. I got a chance to see your script. I don't know what you've written. I don't know how you are going to be scored. So just play it safe when you're solving problems like this. I beg of you. Is that okay? Pull everything out. Let them take the marks they want to give you, and that is all. It doesn't mean write chaps to write the correct thing. Sorry to say that, but let's do the right thing. Okay. So now let's look at what. So you see the reason why we needed a negative, Frank. So you see at the end, the negative is coming to sit here. So if you ignore the first term, it means you are going to ignore this negative. And everything we are looking for may go wrong. Is that okay? So everything that we have done, this is what we have here. And it's very, very perfectly okay. Is that okay? But we have our C here, so the C is attached here. Then at the end of the day, because we are looking at minimizing time, this whole thing can be equated to 0. Is that okay? And of course, if it's 0, we can bring one term to the other side. So that's because one term is negative. So we can send one term to the other side so that we get a positive here, positive here. Now let's look at these two terms that we have here. I'm going to the next slide. If I have a sine and the sine, you know, alternate angles are always equal. So this angle can also be what? Theta what?
Theta 1.
Very good. This angle too can also be theta 2. Now, if I have a right angle triangle like this, and I want to actually find, let's say this is my angle, theta. This is my 90 degrees. I have my A. I have my B. I have my C. And I want to find the angle of this with respect to sine, with respect to cos, with respect to tan. Let's try and find these things. If you have sine, let's say theta, what is going to be it? Sorry, sine theta.
C over A.
C over A. Opposite over what? Hypotenuse. Then if I have cos theta, what is it going to be?
B on A.
So adjacent over hypotenuse.
Hypotenuse.
Now let's look at tan. Tan is going to be what?
C over B.
Okay. C over B. That is opposite over adjacent.
Adjacent.
Now this is what I have. Let's look at, let's say I am interested in only the opposite and the hypotenuse. Because in a situation like what I have here, I can make good use of only the opposite here. And what would be my hypotenuse for this angle?
AP.
It will be AP.
Okay, AP. Is that okay? So if I want to find the sine of the angle I have here, what is it going to be here?
X over AP.
X over AP. And remember, we already find AP using Pythagoras theory. And what did we get? Remember?
We got square root of H1 squared plus X squared.
Plus X squared. And when you look at what we have written here, is it not the same as the one side of the equation here?
Yeah. That's
So
it.
it means we can write our sine theta 1 here. Now let's go to the other side of the equation. If I have an angle like this, where is going to be my opposite and where is it going to be my hypotenuse?
L minus X is opposite.
So my opposite is going to be L
L
minus X, this end. And my opposite is going to be what?
The hypotenuse.
PB. So if I want sine theta, is going to be opposite. That is my L minus X. Is that okay? Divided by what? The PP. And if you remember PP, we said the PP is equated as what? Square root of what?
Square root of
H plus plus
H
into bracket 1 minus X.
Perfect. L minus X squared.
Squared.
And it's the same as the second term that we have here, which of course we can write what? Sine what?
and theta 2.
Sine theta 2. Now we have sine theta 1 equals sine theta 2. One important thing is anytime we are dealing at very small angles in sine, it means that sine theta can be equated as the same what angle, that is the theta. Is that okay? So it means dealing with very small angles, we can equate our sine to be equal to what? Theta 1. And equate this one to be also what? Theta 2. And do you remember this, the law in reflection?
Yes, in this law.
Very good. That this is a law under reflection. The angle of incidence is equal to the angle of what? Reflection. So Fermat actually used this to perfectly prove the law of what? Reflection. That is the whole issue about Fermat's principle. Are we okay? Any question? Should I go on? Perfect. So now let's go on. So this is the whole thing. Is that okay? So now we've proven that the angle of incidence equals to the angle of what? Reflection. We can also do the same thing. You know, when it comes to refraction, the law is not sine angle equals sine angle of incidence equals sine angle of. The formula is n1 sine of theta 1. Remember Snell's law equals sine n2 sine of theta 2. So something like this that we have, something like this, we have to be able to prove using this to get this formula. Is that okay? When you start proving, this is what we are expecting to result to. Please, are we okay? I'm not going to touch this. I have given you a hint what we should be expecting. Is that okay? And we've taken our time to also go through the reflection. So try your hands on this, I beg. You may be given any of them, either the reflection or the refraction. I don't know. Is that okay? So let's try and be confident with the two. Or you may not be giving any of them at all. Who knows? So let's just try our hands on it, just in case you see it in the exams. Is that okay?
We are praying.
Come again.
I said we are praying that we not see any of them.
Let's pray. Okay. Okay. But I think exams you don't solve everything. You are given options. I think this time around the last time you were given about 4 questions. No, is it 3 questions?
Yes,
No,
sir.
4 questions to
Yes,
solve
sir.
three. Mhm. So if you think the one that is given to you is not really confident enough, you can still choose the other that is available. But sometimes these kind of questions it comes and it has a very big mark. So imagine you're able to solve this one very well. You are good to go. You know, you don't have a
So,
little problems there.
so we will continue to practice it. So thank you.
Mm, mm, mm.
Mm.
I'm expecting that, say, Christopher, in your this thing when it comes, you solve this. I'm expecting you to solve this.
Yes, sir. Yes, sir. I will practice it continuously.
Mm, okay. But Frank is good at this, so in case you have any issue, you can just call on him so that he helps.
Yes,
Is that
sir.
okay?
Okay. Yes, sir.
Uh, please a minute. Let's hold on. I'm coming. I think we can even go for like 10 minutes break and come back and come and continue. Is that okay with everyone?
Yes, sir.
Yes,
Yes, sir.
please.
So it's 9:16. By 9:30 then I start. Is that okay?
Yes,
Okay.
sir, sir.
Thank you.
Hello, 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 guys.
Hello, please, can we continue?
Yes, sir.
Yes, sir.
Yeah. Okay, so this we've controlled it, we are done. So now let's look at dispersion. You know, I told you that the last time what we used to know that dispersive light is only like a prism, but in other ways, there are a lot of dispersion to that happens. Is that okay? And even interference brings dispersion. I told you that last week I was explaining the peacock colors that we see, the colors we see on the third road when it rains a bit. And even with naturally, God gives us rainbow. Is that okay? That beautiful pattern of colors. That one too is another way of dispersion. You know, when we are talking about dispersion, we are talking about the different colors we are separating from a white light. So white light composed of all the colors we blended them together. But in a situation where we are trying to separate them, that becomes a dispersion. And you know, one important thing that brings about dispersion is the speed that the individual travels. So because one tends to move very faster than the other, it tends to bend more than the other. And at the end of the day, we get that nice pattern of colors. You know, when this thing actually came, it was very confusing. I told you the last time that even Isaac Newton was contemplated on a situation like this that why is it possible that I get white light pass through a prism, then I get colors. So he performed this experiment where he had two glass prisms, one at one angle and one turned over. A beam of light is allowed to pass through. And right after passing through, we get this nice pattern of colors. He brought another beam of light, and the mentality is to converge all of them through that same prism and see if we can actually get our white backlight. The white back that we gave it to, can we get it back? Through that, it will prove that, okay, it is the mechanism that goes on in there that disperses the light. It's not any medium in the prism that is causing the dispersion of light. Fantastically, he saw that. Is that okay? It means the dispersion of light is not particularly because, let's say, we have a material in the prism that is being induced or something. Is that okay? Before we get the dispersed light, it's dispersing because of the different speed it travels, the different dispersive medium that it has, and at the end of the day, we have dispersion. And at dispersion too, there is a question that we tried. We can find for something we call the dispersive power. We can find for something we call the angular dispersion. Is that okay? So the last time we went through this, and I was trying to explain to you that we know this formula already. This is for finding refractive index. Is that okay? So if we have a refractive index, we can find sine into brackets A plus B. That is, this one is the deviation. We have A to be the angle of the prism divided by 2. And we have sine of this. Very, very okay, right? But we can also look at it in a different perspective, where if the angle that we have, again, I told you this before, that is small, we can ignore the sign. So that at the end of the day, we have only these two terms here. Is that okay? That is what I have here. And if we have to do change of subject and all, we can also find the rearrange it so that at the end of the day we have our refractive index multiplying the A equals A plus the dispersive power, the minimum deviation. So what we are just doing is to multiply this one by our term here, then leave this term behind, so that at the end we have our minimum deviation A divided by 2 equals A plus our minimum deviation divided by 2. So these two cancels these two, right? At the end of the day, we have this term. And that is what I have at the top here. Is that okay? I can bring this term to this other end here. And when I finish, I'll substitute A out so that at the end, I'll get the minimum deviation to be this whole term. Is that okay? Because when I send the A to this term, I'll get my refractive index multiplying A minus A equals the minimum deviation. I will substitute A out. Is that okay? And I have to know that when I get something like this, and I remember a question like this came in your exams, and I think you were asked to just find the dispersive power, right? So what you're supposed to do is to just add and divide by the other term, other refractive index. Do you remember a question like this?
Yes, sir.
Please.
Yes, sir.
And this thing, I think when you finish, you just get some free 5 marks, and that is all. Very, very free. And this one is free 5 marks. Is that okay? So this is what we are looking for. This is going to help us find for the minimum deviation for each wavelength of light that we have there. We can find for yellow, we can find for red, we can find for orange. In fact, any color that we want. So this is for the violet, this is for red, the extreme ends. If we want to find the deviation between all of them, from the red to the, say, violet, that is where we subtract it like this. Is that okay? And at the end of the day, we can get a term like this. If you are to subtract this whole term that we have below from the first one, this is what you are going to get. But nevertheless, we have to also remember that in a situation where we want to find the dispersive power, the dispersive power is always adding the extreme ends and dividing by the wavelength at the middle. Is that okay? And of course, we can find it by using this minimum deviation. And it's either we are using the minimum deviation or we are going to use the what? Or we are going to use the refractive index. Either of them is fine. Is that okay? So a question can be given to you where they give you these terms or they give you these terms. Either way is fine. Is that okay? So this is for finding the dispersive power. And here we have our refractive indices. Some people were doing a mistake. They were not bringing the -1, which is very wrong if you do that. Is that okay? So you have to subtract it from the extreme end. Bring the minimum deviation for this one and subtract it from this one. These are the refractive indices. If you are given the refractive indices, you are trying to go through this way. If you are given the minimum deviation, you will go through this way. So it's two different terms. Minimum deviation is through this way. Refractive indices is through this way. And I think the mistake was from this end. The question gave you the question gave you refractive indices, 1 point something, 1 point something, 1 point something. You have to use this procedure. Is that okay? If you use this formula, you are going to get it wrong. Is that okay for finding the dispersive power? Can I go on?
Yes, sir.
Perfect. Now, we also went through rainbows, and we said it depends on where the observer is, the light traces, and where we get the formation. Always, we expect the observer to be between the light trace and the water droplet. Is that okay? So if you are standing like the observer that we have here, the observer is here, the light is coming behind from the observer. We have water droplets in front of the observer. Is that okay? And even with this one, we said we have two types. We have a primary rainbow and we have a secondary rainbow. Is that okay? Is that okay? And we said that for the primary rainbow, the most important thing is one, the formation and the angle that we are getting. Is that okay? So you can see that the primary rainbow it starts from red and it ends at what? Violet. You understand? And for the secondary rainbow, it starts from what? Violet and it ends at what? Red. So anytime you see a rainbow and the first color that you see at the top is red, you should be able to explain to people that are around you that, oh, this is a primary rainbow, this is a secondary rainbow. And even with the two, primary rainbow is very, very visible. Secondary rainbow is a little bit not visible. Is that okay? So you can use that one to differentiate. And the last thing too is the angle. Is that okay? The angle of formation for the two angles, the two rainbows. One is forming around 54, one is forming around 51, one is forming around 40. The primary is around 40 to the eye level. The secondary is forming around what? 54. So it means the primary is mostly down and the secondary is mostly what? Up. Is that okay? So that's the difference between primary and. And we also discussed the mechanism that goes in the water droplet. Is that okay? So we have some total internal reflection happening. We have some refraction happening. We have some reflection happening. We have some emergence of rays also happening. And all these things we've spoke about it. Is that okay? So it's very important that you know. And there's a question here. I think say we never more. And let's look at lenses. Let me try and see if I can finish lenses. So lenses too is very important phenomenon because you know when we are talking about these lenses, it doesn't behave as normal as the normal glasses is going to behave. We don't want the normal properties of a plane mirror. We want a different property of these planes. So we have some curved lenses, we have some curved in, curved out, and all. They are all optical components. Now we have something we call the convex, we have something we call the plano-convex, we have something called the biconcave, we have something called the plano-concave. We will look at all of them. But the most important thing that we have to know about lenses is their parts. Is that okay? We have a place at the center, we call it the optical center. We have a principal axis, we have something called the center of curvature. Is that okay? When we are talking about lenses, lenses has two center of curvature. It has C1 and it has what? C2. When we are talking about mirrors, curved mirrors, how many center of curvature does it have? Do we know? Do we know? Hello.
Hi.
I'm saying for a lens has center of curvature to be two. One is sitting here, one is sitting here. What about a curved mirror? Curved mirror like either a convex mirror
So
or
it has one, just one.
it has only one. Is that okay? Which is very important that we know. So the same properties that we have for these lenses is the same one that we have for the mirror, the curved mirrors. So as we have it here, we can have our center of curvature sitting around here. We have something we call the principal axis 2 in the curved mirrors. We have something we call the focal length or point of focus. That one, where will it be in this diagram? Any idea? Any idea? Where is going to be our point of focus or our focal length? From the diagram I've shown.
Focal length.
Okay. So that is always between the center of curvature and the optical center. Is that okay? So it's mostly at the center here. Is that okay? So if we have a plane mirror tool like this, if this is our center of curvature, and this point here is the optical center, we expect our focal point to be here. That is our F. Is that okay? So from the distance here, that is our center of curvature. The formula is always C equals what? 2F. Is that okay? So if we divide the center of curvature by 2, we're supposed to get our focal point. Is that okay? Now, these are basically the part of the lens, and it's transferable to the part of the curved mirror. Is that okay? There's one thing that you also have to know, that anytime a light rays or a beam of light passes through this kind of mirror, we let it's supposed to focus at this point, and that is our focal point, what I just said, and that is called the focal length. From that distance of the optical center to that point is the what? Is the focal length. So if it's a converging lens, this is how we expect it to behave. A converging lens is always like this. Is that okay? And a divergent lens is drawn like this. Two plano concave that is merged together. Is that okay? Anytime we have rays passing through this kind of a lens, we expect it to meet at a point. Convergent lens, as the name says, so it all converge at a particular point. Is that okay? A divergent lens means anytime the lens, a beam passes through like this, we expect that it will diverge away. Is that okay? We expect that it should diverge away. And the virtual point that we have behind here will form a point of focus, which we will talk about it later when we see it somewhere. Is that okay? So these two things are very important that we know. So we have the principal that is passing through the center. We have our point of focus or principal at focus. And the distance between this end to this end, that is the optical center, and the point of focus or the principal focus is called the what? Is the focal length. Any question? Okay. Now there's a very common formula that we use for these lenses. Come again. Okay. So the common formula that we mostly use is this. And I think a question 2 came in your exams where you were giving some parameters like the focal length. You were giving some parameter like I think the object distance. I think we even have that question here. Maybe I don't have it, maybe I have it in other slides. But I think I stand to be corrected, but I think you were given a question like this. And at the end, you were asked to find the image distance, you were asked to find the magnification. Then when you finish, describe the properties of what you have gotten, whether it is virtual or real, it is magnified or diminished, or it is upright or inverted. Did you see a question like that? And how did you do it? Were you able to go through well?
Yes, sir. I think it came in the end of exams.
Yeah, it's the end of something that I'm talking about. That there was a question like that,
Yeah.
right? And I'm asking
Yes,
if
sir.
you're able to do it.
Yes, please. I was able to do it. I remember one of the answers, if it is negative, it means it is a virtual image.
Perfect.
Yeah.
Okay, that's fine. So now let's go through. So this is the one important formula in image. Is okay in lenses, and we call this one the lens formula. It is used for It is used in both the lenses and the curved mirrors. Is that okay? And for your information, you should be able to. No, I don't have this in the slide, but you should be able to know that anytime that we place an object at a particular position of a mirror, it gives a different form of what? Of images. So if this is my curved mirror, this mirror is called what? Do you know the name of this kind of a mirror? Do we know the name of this kind of a mirror? So the mirror, we have one. One is like this, and another one too. And this is the coated side. And we have another one like this. And this is the coated side. What's the name of this kind of a curved mirror?
I said the first one is concave, second one is convex.
Perfect. So this is a concave mirror. This is a what? A convex mirror. If this is our center of curvature, D, and this is my focal length, F, it means that if anytime I place an image at different positions here, an object at different positions here, I'm going to get a different form of an image. If I place it here, it's going to be different. In fact, if I place it on the F, it's going to be different. If I place it beyond the F, it's going to be different. If I place it at the center of curvature, it's going to be different. If I place it beyond the center of curvature, it's going to be different. Is that okay? And we have to know this very well. It's the same as a mirror. I didn't add this in the slide, but just read about it. Okay. At each position where we place it has a different form of image that it will give to us. And there's even a way that we can draw to trace this kind of an issue to see where it's going to be formed. Is that okay? So this formula is very important. The F here is the focal length, the V here is the image distance, and the U here is the object distance. We are given, we just substitute, and that is all. There's another one too that we call the power of a lens. And the power is just measuring the degree of convergence or the divergence. And it's simple, it's just about finding the reciprocal of the what? Of the focal length. And the unit is what? Diopter. So let's take care of that. So yes, Thomas, your hands is up. Ask your question. Yeah, Thomas, please, I'm listening.
I said, please, I'm not raising my hand.
Oh, okay. So, and we have magnification too. In fact, magnification can be calculated in size and in distance. Is that okay? If you're using the sizes, you can just do image size over object size. But if you're using distances to calculate, what is going to be the formula for magnification? Any idea?
The question again, please.
This formula is for finding the magnification in terms of sizes. Is that okay? Image
Yes.
size or object size. But we can use V and U to also calculate for magnification. What is going to be the formula?
M is equal to V on U. That's image distance over object distance.
Okay.
So I think the image distance is a negative. So negative image distance over object distance.
So it's going to be negative V on U. Is that okay? If you are using distance to calculate. So let's be careful about this. Now let's look at the lens maker formula. This formula is relatively very important. Is that okay? And general physics I didn't do. Here too, I will not go through with you. Is that okay? We will just go to the very last end. Those who will be doing the physical optics, then we will dive more into it. So the lens maker formula is just comparing if we have a lens like this, then we have our principal as is passing through. We have 1 center of curvature here, 1 center of curvature here. We are interested in only these 2 center of curvature because you can imagine the lens to be something like this that we've merged them together. 1 here and 1 here. It means that we can get a different form of a center of curvature between the 2 of them. But it's the 2 of them that is going to give us a very common focal length or a principal focus, that is the F. Is that okay? And that is very important. So we need to find for the R1, we should be able to find for the R2 before we can find for the what? For the F. That influences the F a lot. So we have this as what? Our refractive index minus 1 into brackets 1 over what? R1 plus. Here's 1 over R2. Is that okay? Which is very important. So this formula, I just want you to keep this formula in your head. Is that okay? We will deliberate on it when we are doing physical optics. Then we have combination 2 of lenses. All these things we've done it to, so it's just a recap, one way or the other. We can combine lenses to form a focal length of choice. Is that okay? So I have lens 1, lens 2, lens 3, then I merge them as I have it showing you right now. If I have something like this, I can find the total focal length. And it's simple. If I want to find, I have 1 lens here. I have another lens. I have another lens. So if I want to find the total focal length, it's going to be F, this F1, F2, and F3. So this is going to be my F1, F2, and F3. And that is going to be give me the total focal length for this particular one. Exactly. So if you are given only 2, there is F1, F2. If you are given 5, F1, F2, F3, F4, F5. Is that okay? This formula is what is going to help you. And there's a question here. And I think this question, we've tried it before, so we'll just go on. And I think this brings us to the optics side. Any questions so far when it comes to reflection and refraction? Any questions so far? So you see what we have done.
Sir,
It's not difficult. Yes.
please, kindly touch on where we have to have an image being virtual or real or inverted.
So they all depends on the negativity of it. Is that okay? If we have negative or we have positive, that is going to define whether it's going to be real or virtual. But in case we have, please hold on. You people, we finish. We go break. When the time will come. Sorry. So that is going to the negative is going to define the real and the virtual. The magnification, that is it being big or diminished, is going to define by the value of the M. If you have a value more than, let's say 1, it means it's magnified. You have value less than 1, it means it is what? It's diminished. Is that okay? and how, whether it's standing upright or inverted, that one too is going to dependent on the negative of it. Is that okay?
Okay.
Mhm. So the only thing left for us to do is the heat. The heat, I will not tackle it right now. I'll look at it next week. Then we use the flowers for the heat. We'll talk about the nature of heat, solve a lot of problems on it. Look at the calorimetry, talk about latent heat of fusion, look at ideal gases. They are not plenty. Heat, we will not talk a lot on it. Then that will be all. So hopefully, I'm sure next week's stuff we may use only 2 hours to do, but I will try and we will go through all the questions under heat so that you'll be very, very confident with the questions and how it's posed. Is that okay? So if there's no question, I will want to end the class if you don't mind. Then we use the
Hello,
What the scattering and the distance, you say we'll go back there. I don't know. No, or not
Yeah,
today.
not today. The heat I have it's not plenty, so and that one I have to prepare slides on that. Sincerely, I have not actually done it. Is that okay? So I don't want
So
to.
that take me to my second question. The updated slides. I don't know if you're done with it.
Okay, so I've updated the atomic physics part. That one I can send that one to you, but I was thinking of finishing the optics before I send. But anyways, I can send that one to you by tomorrow. Then maybe
Yes,
I'll
sir.
pick my update the optics part. That one it will take a little time unless we finish with next week's class before I can send. Or maybe getting to Wednesday, Thursday, I'll be done, hopefully. By adding the interference and the scattering, the diffraction. We will not go deep. It will just be the surface, but I'll still have to add it for you guys. Then the heat part, I will not update. We'll just use it like that. Is that okay? So it's just the small things that I'll update.
Okay, so can we get everything like your slice, everything from A to Z?
Yeah, that will not be now. That will be maybe by Wednesday.
Okay.
So then we are waiting for it.
Yeah, I think that done, but
Then
it's
wait
not.
for it on Wednesday so that we can get everything.
Yes, by Wednesday I'll give you everything. Is that okay? So yes. So please solve past questions. Very important. Go through the slides questions. Then just understand. Is that okay?
Sir,
The past questions. We don't always get access to the past question. I don't know if you can talk to Doc and
No,
you send it to us.
you will not get access to past questions. The only people that has access is your past students, like those who finish the program right now. When you go and ask him, they do a lot of things, so it will confuse him. He may give you some questions that is not even related to what you are doing. Is that okay? So they only look for people that recently did it, and take their questions. Is that okay? I think that is the best way.
Sir, please, I have a question.
Yes, sir, partner.
Suppose a ray of light moves from air or passes from air through a medium, let's say water, and emerges. Is the incident ray going to have the same speed as the emergent ray?
So we have a ray of light that is incidented on water. Now
Yes.
it's traveling in air and it entered water.
Yes.
If it entered water, it's not emergent, it is still refracted. If it exits from the water again to air, that is what is called the emergent.
So that's what I'm talking about.
Very good. So
is it going to have the same speed as the incident ray?
Yes, it's going to be the same speed as the incident ray. So the speed that is using it to travel in air, let's say it was 3. If it enters water, it will go down to 2 points, let's say 8. Then it's in water, the same speed with 2.8. It emerges out from the water to the air again, the same air. It will go back to 3. Is that okay?
Is there not going to be any energy loss while it was in the water?
Interestingly, no. So when it comes to refractive indices, it has no influence on in terms of their energy and let's say their frequency or anything. The only thing that is bringing here is it's causing the slow movement of the thing, the ray. Is that okay? So that is why Newton is good you've brought this question up. That is why Newton actually performed that experiment to see whether in a prism there's something in the prism that is causing the emergence of these nine scholars. Is that okay? So you can see that after that he changes the position and he still gets to the white light. Nothing happens to it at all. Is that okay? So the refractive index doesn't influence it in terms of energy. The only thing that it influences is in terms of heat.
Okay. Thank you.
Hello,
Mm.
hello, sir.
Yes, Al Hassan, I'm listening.
Please, with the magnification issue,
Mm.
in case I want to know the whether it is inverted or upright, is it
Mm.
good I use this formula like M is equal to negative V over U?
Yes, you can use
Okay.
that formula, negative V over U. I think we spoke about it. Yes.
Okay. Thank
Mm.
you.
You're
All
welcome.
right. Thank you. All right.
Any different question? Okay. We've ended early today. So let's go with, if you have any question, just come and write it for me, then we'll tackle it. There's another thing too. I may not be around this coming weekend. I don't know for now. But in case of anything, I'll pardon with you, then do the class the following week when we enter that weekday, maybe Monday, Tuesday, Wednesday. Is that okay? It's a plea then. I don't know.
Yes, sir.
I have not figured it out. I have a trip to go on Gorwell on Sunday, but I don't know if that Saturday I'll be available or I'll be on my preparations. If I am around, I'll do that Saturday. If not, I may plead them maybe when I go on the trip where is that okay? Then I'll do the class.
Okay, sir.
Thank you very much. So please, we'll hear from each other. Is that okay?
Good.
Have a
Okay, thank you.
Please, colleagues, if somebody have any past question, we can
Frank,
drop it on the FCC platform.
Frank,
Yes, sir.
Frank.
Yes,
Please,
sir.
the ferment, this thing, write it and put it on the page. Let's see something there.
All right, sir.
Yes.
Hello.
Frank,
Yes,
yeah.
sir.
I'm not on the
But you are
physics
doing
class.
business measure. Why are you here?
Hello.
Yeah, we also do.
I said you are
Hello.
a business major student. What are you doing here?
The same thing. We are also doing the same thing.
I think you are doing a matrimonial something like that.
No,
Yeah,
it's
yeah,
two.
we are still doing that one. We are
You
doing
are
both.
doing that one in addition to this one.
Yes.
Okay.
But I say I'm the one to same one, so no problem.
And I'm ready. Me kura. Back on me try as I go. Me join.
Okay. Yes. Yeah, man.
If you have any past question, you can drop it on the.
Hello. Hello.